Alright, in this example we're given a compound pendulum that swings within this pendulum clock, and we want to find the equations of motion for the pendulum in the clock when it's swinging freely. So let's solve the equation of motion using our general form of Euler's second law, and we'll solve it about point O, which is fixed. And so starting with the general expression, we see that the acceleration of O with respect to O is equal to 0, so this entire term becomes 0. And what we have here is another useful form of Euler's second law, which is always true, is that when we're using an inertially fixed point, then the angular momentum, the time derivative of the angular momentum about that inertially fixed point is equal to the moments about that fixed point. So we create a system diagram in which the pendulum is swinging. We've seen this before. We have a single degree of freedom theta, but it's made up of two bodies, which has a center of mass of the rod that composes the top portion of the body, and the center of mass of the disc, which composes the bottom portion of the body. We're given these dimensions here on the right. The rod is L long and then A wide, and then the disc has a radius of big R. So like any other problem, we need to set up reference frames. And for this we have two frames because we have one rotational degree of freedom, an inertial frame and a body frame. Our inertial frame E1, E2, and E3. In E1 being along O to the center of mass of the disk, so G disk, E3 out of the plane, and then E2 the cross product of E3 and E1. And then for the body frame, B1 is along this for any theta, E3 out of the plane, and then B2 is the cross product of B3 and B1. We have a transformation table, which is the standard table that we've used before, and then of course our angular velocity of the body frame as observed in the inertial frame is theta dot in the B3 direction. We're solving for each of the parts that go into our expression for Euler's law about a fixed point, and so let's start with the angular momentum about the fixed point O of our rigid body. We said earlier that the angular momentum about any point is the moment of inertia about that point multiplied by the angular velocity as observed in the inertial reference frame. But we don't know what I sub O is. So let's find the moment of inertia about the point O. To find the moment of inertia of the entire composite body about point O, we'll find the moment of inertia of the disk about O, and then add to that the moment of inertia of the rod about O. So let's work those individually. Let's start with the rod. So the moment of inertia about O of the rod is we're going to start with the moment of inertia about the center of mass of the rod, and then we're going to add to that the mass of the rod, and then multiply that by RO with respect to the center of mass of the rod. We'll just call that G sub R squared. We can look up in the back of the book that for a non-slender rod, the moment of inertia about the center of mass of the rod is equal to m over 12 of L squared, the long dimension, plus A squared, which is the short dimension. The position vector, R of O with respect to G sub R, we see here goes from this point to that point, which now with a reference frame drawn on our rigid body, we see that to go from the center of mass of the rod to point O is negative L over 2 in the B1 direction. Also I should point out that we drew our reference frame at point O instead of the center of mass in this situation because we didn't know where the center of mass was. Now we plug in these expressions into our parallel axis theorem to calculate the moment of inertia of the rod about point O. And we obtain the expression of mr divided by 12 multiplied times the quantity L squared plus A squared plus the mass of the rod mr multiplied by, and this is the norm squared, so L squared divided by 4. Next let's calculate the moment of inertia of the disk about point O. And so I O of the disk will be equal to the moment of inertia about the center of mass of the disk plus the mass of the disk multiplied times the norm r of O with respect to the center of mass of the disk, so G sub D squared. We look at each individual component, the first being the moment of inertia about the center of mass of the disk, and this is equal to 1/2 the mass of the disk, r squared, so our radius is big R squared. And now we need the position vector of RO with respect to the center of mass of the disk. And by looking on our diagram, we see that this distance from the center of mass of the disk to O is the distance L plus R, and it's in the negative B1 direction. So negative L plus R quantity in the B1 direction. And so we take each of these expressions, we plug them into our expression for the moment of inertia of the disk about point O. Now we obtain this value for the moment of inertia of the disk about point O, where we add together the moment of inertia about the center of mass, plus this term, the mass multiplied times the distance squared. And now when we add these together, we get a really long expression for the moment of inertia of the entire compound pendulum of composite disk and composite rod about point O. And we can apply a simplifying assumption here, where if L is much greater than A and L is much greater than R, so essentially saying that A and R are small relative to L, and this makes it different because recall that moment of inertia is more dependent upon the length term than it is the mass term, that what we can do is we can cancel out our A's and our R's, and this leaves us with the moment of inertia about point O is approximately equal to mr divided by 3 plus md and L squared. So it only becomes a function of the length of the rod, but we still consider that we have the mass of the disk, but really this is essentially saying that the mass of the disk is at the end of the length of the rod. And then we retain our mass of the rod 1/3, but then we've taken out the width A, which is also the same as the moment of inertia of a slender rod about its end point. So now with the simplified expression, we have the angular momentum about point O is equal to mr over 3 plus the mass of the disk, L squared, theta dot, and then the time derivative of the angular momentum about point O, inertially fixed point, is m sub r divided by 3 plus m sub d, L squared, theta double dot. And so now we have our entire left-hand side of our equation. Now for the right-hand side of the equation, which is the moment due to all the external forces about the point O, we need to draw a free body diagram. And on the free body diagram, we'll include both our rod and our disk. Each of these have a force due to gravity, so this is the mass of the rod, G, and this is in the E1 direction. And then there's a force due to gravity on the disk, so this is m sub d, G, also in the E1 direction. And then the other forces we have are a normal force, I'll call this N2 in the E2 direction, and then we'll say N1 in the E1 direction. The moment about point O will be due only to the force due to gravity on the rod and the force due to gravity on the disk, and so it's the position vector of the center of mass of the rod with respect to O crossed with the force acting on the rod, and then the position vector of the center of gravity of the disk with respect to O crossed with the force of gravity on the disk. We find the position vectors that we need to solve this moment equation, and then insert them all into the moment equation where we have L over 2 in the B1 direction crossed with m sub r G in the E1 direction, plus L plus R in the B1 direction crossed with m d G in the E1 direction. We've expressed this in a mixed basis. We have a B1 crossed with an E1, so that means we need to convert either to the B basis or to the E basis. And then after converting and doing the cross product, we get that the moment about point O is equal to negative g sine theta multiplied times L over 2 multiplied times the mass of the rod minus L plus R quantity multiplied times the mass of the disk. And this is in the E3 direction. And so then substituting in for our left-hand side and our right-hand side, we can convert the E3 to a B3, and then we get the scalar equation, which has the time derivative of the angular momentum scalar, and then the moment about O and its scalar. We solve for theta double dot for the equation of motion, and then with this we now have an equation of motion which has buried in it, always look in these pendulum problems, it has buried in it our simple pendulum, g sine theta, negative g sine theta over L, but it has all these additional terms which are modifying the inertia to make it this compound pendulum made up of composite bodies.